Hello everyone, good day. I am Quizan with my partner Marichel Olingay, and this is our presentation about networking essentials topics. And the topics that we are going to discuss for today are the following: OSI and 802 networking models, IEEE 802 networking specifications, brief recap on the topics, introduction to network essentials, networking media, and network interface cards. Introduction. In this report, we will explore the Open System Interconnection OSI reference model for networking, which explains how networks behave within an orderly 7-layered model for network communications. Then we will learn more about the IEEE 802 networking model and the standards that surround the 802 designation. And finally, we match the two models against each other to see how they fit together. And note where networking hardware plugs into each model. In clearer sense, this report tells us how the network is worked behind the surface we know, like how we detail the process of cooking fried chicken, delivering a mail, or how we do our daily morning and night routines. These frameworks lets us understand and explain detailed process on how network works as network and how the layers are communicating and connecting with each other. The Open System Interconnection OSI reference model proposed by the International Organization for Standardization ISO in 1984. This model is sometimes referred to as the ISO or OSI reference model. Is a framework for networking concepts where the idea of the OSI model and its 7-layer approach to networking is being widely used as reference for network operations. It is also very helpful in determining certain problems in a network and easy location for specific troubleshooting. Now, let's talk about layers. Layers conveys the essence of the OSI reference model. Essentially, this model's foundation rests on the idea that networking can be broken into a series of related tasks, each of which be conceptualized as a single aspect, or rather a layer, of the communication process. This process breaks the complexity of network communication from applications to hardware into series of interconnected tasks and activities. Then, even though the relationship among these tasks and activities persists, each individual task and activity can be handled separately and its issue solved independently. Computer scientists like to call this approach as divide and conquer because it creates a method to solve big problems by deconstructing them into a series of small problems into individual solutions. Simply put, the OSI reference model breaks networked communication into 7 layers, and these are the application, presentation, session, transport, network, data link, and physical. To easily remember these terms, just remember the phrase, all people seem to need data processing. To fully comprehend the model's function, it's necessary to understand how it behaves as a whole. At the outset, any computer that can access a network must be endowed with a protocol stack, also known as a protocol suite. Protocol stacks provide the softwares that enable computers to communicate across a network. Currently, the most common protocols stacks include the following: Transmission Control Protocol or Internet Protocol, or as we all know, TCP and IP, Internet Packet Exchange, Sequence Packet Exchange or IPX or SPX, NetBIOS, Enhanced User Interface or NetBU, AppleTalk, and lastly, Systems Network Architecture or SNA. These protocol stacks, combined with drivers for whatever network device are attached to a computer, provide the crucial network link that permits applications to communicate with the network. Taken as a whole, protocols plus drivers equals to network access. Each individual layer in the OSI model has its own set of well-defined functions, and the functions of each layer communicate and interact with the layers immediately above and below it. In the reference model, layer construction follows an abstract concept called peer layers. That is, each layer on one computer behaves as if it were communicating with its twin on the other computer. This is called logical or virtual communication between peer layers. On its way down the stack, before the data get passed from one layer to the next, it is broken down into data units, sometimes called packets or payloads. The official OSI acronym is PDU, sometimes interpreted as Protocol Data Unit, or Packet Data Unit, or even Payload Data Unit. The PDA is a unit of information passed as a self-contained data structure from one layer to another on its way up or down the stack. At each layer in the stack, the software adds its own special formatting or addressing to the PDU to allow delivery of its payload across network. This special formatting or addressing added to the PDU is referred to as a header, and the process of adding this header is called encapsulation. At each layer, software reads its specific PDU data and performs any additional processing required. It then strips its specific information, the header, from the PDU and passes the PDU to the next higher layer. This process of stripping the header from the PDU is referred to as the encapsulation. Now let's take a look at what PDU protocol and devices this layer have. And to fully get the idea on which PDUs, protocol stacks, devices, and functions each layer have, we will going to see 4 tables that each show information respectively. Let's start with the first table, the Protocol Data Unit or PDU. In this first table, the 7th, 6th, and 5th layer have the same PDUs in them and they are called data. In the transport layer, the PDU is now called segments. In the network layer, the PDU is now called packets. In the data link layer, the PDU is now called frames. And lastly, in the physical layer, the PDU is now called bits. They're slowly transforming each layers as they pass through each layers. Now let's go to the second table. The second table is categorized in the Internet Protocol suite or stack they have been used. In this second table, you will see the Internet Protocol these layers are using to be able to operate. In other words, in this table, we will see the software components that operate and facilitate each layer. As you can see in the table, the application, presentation, and session layers utilizes the same protocols. Same goes with the data link and physical layers, and the rest uses different protocols respectively. And now on to the third table. This table is categorized as the devices. In this third table, you will see the devices used that enables these layers to functions, and these devices includes tangible and intangible devices. And lastly, the fourth table. This fourth table is categorized as the OSI layers functions. In this fourth table, we will see the specific actions that these layers perform individually. The application layer is responsible for transferring information from program to program. Presentation layer is responsible in handling text formatting and display code conversation. Session layer establishes, maintains, and coordinates communication. Transport layer ensures accurate delivery of data. The network layer determines transport routes and handles the transfer of message. Data link handles codes, addresses, and transmit information. physical layer manages hardware connections and handles sending and receiving signals. Here are some things you need to remember in each layer. The application layer also handles general network access, the movement of data from sender to receiver, and error recovery for applications where applicable. Presentation layer, a special software facility known as a redirector operates this layer. The redirector intercepts requests for service from the computer. Requests cannot be satisfied locally or directed across the network to whichever network resource can handle the request. The session layer also provides synchronization services between tasks on both ends of a connection. The transport layer also handles flow control. Flow control ensures that the recipient of transmitted data is not overwhelmed with more data that it can handle. The network layer is also the traffic cop for network activity and handles packet switching, data routing, and congestion control. Network layer downsize packets coming from a medium that handles larger PDUs to a medium that handles smaller packets. This process is called fragmentation. When data arrives at the receiving end, its final destination, the network layer reassembles the downsized pieces into their original packets. Data link layer is responsible for detecting errors in the transmission of frames and discarding those frames that arrive containing errors. The data integrity check, called cyclical redundancy check or CRC, is a special mathematical function based on the bit patterns in the frame, sent as part of the frame itself. The CRC is recalculated on the receiving in the same from it was sent. The physical layer handles the intricacies of transmitting the pattern of bits that represents a data frame from sending to the receiving computer. Even those bits are arbitrary at this layer. Encoding is the representation of zeros and ones is a physical signal, such as electrical voltage or a light pulse. The components of a network working at the physical layer include all the cables and connectors used on the medium, plus repeaters and hubs. The IEEE 802 Networking Specifications. It is a collection of networking standards that cover the physical and data link layers specifications. Standards are published documents that establishes specifications and procedures designed to maximize the reliability of the materials, products, methods, and/or services people use every day. The Institute of the Electrical and Electronic Engineering, or IEEE, launched an effort to define a set of LAN standards to ensure that network interface and cabling from multiple manufacturers would be compatible as long as they adhere to the same IEEE specifications. And this effort was called Project 802 to indicate the year 1980 and month February of its inception. Since then, the IEEE 802 specifications have taken firm root in the networking world. The Project 802 concentrates its efforts on standards that describes the physical elements of a network, including network adapters, cables, connectors, signaling technologies, media access controls or MACs, and the like. Most of these reside in the lower two layers of the OSI model in the physical and data link layers. In particular, the 802 specification documents describe how the NICs may access and transfer data across a variety of networking media. They also describe what's involved in attaching, managing, and detaching such as devices in a networking environment. IEEE codified the various efforts as part of Project 802 in a number of standard categories, numbered 802.1 through 802 802.20 as shown in this table. And now let's go to IEE 802 extensions to the OIS reference model. The IEE 802 specification expanded the OSI reference model at the physical and data link layers, which define how more than one computer can access the network without causing interference with other computers on the network. The 802 standards provide more details at these layers by breaking the data link layer into two following sublayers. First, Logical Link Control LLC for error recovery and flow control, and second, the Media Access Control or MAC for access control. The Logical Link Control LLC controls data link communication and defines the use of logical interface points, called service access points or SAPs, that other computer can use to transfer information from the LLC sublayer to the upper OIC layers. The LLC is also responsible for error recovery in some situations. There are several models of LLC operation. Some models require the LLC to detect and recover from errors in transmission. This function is largely implemented in hardware on the NIC. And now let's go to the Media Access Control or MAC. The Media Access Control or MAC sublayer provides shared access for multiple NICs with the physical layer. The MAC directly communicates with a computer's NIC and is responsible for ensuring error-free data transmission between computers on a network. The data link address burned into every NIC's PROM is called a MAC layer address because it operates at this sublayer of the 802.2 specification. This picture shows the IEEE 802 specifications mapped to the LLC and the MAC sublayers to provide specification for LLC, CSMA or CD networking, token bus networking, token ring networking, and demand priority. Summary: the OSI reference model and the IEEE Project 802 define a frame of reference for networking and specify the lower layer behaviors for most networks in use today. Together, these models describe the complex processes and operations involved in sending and receiving information across a network. Second point, the OSI reference model breaks networking across 7 layers, each with its own purpose and related activities from the bottom up: physical, data link, network, transport, session, presentation, and application. This reference model explains most networks, even those that predate its introduction. Most network products and technologies are also positioned in terms of the layers they occupy. The layers help describe the features and functions that the products and technologies deliver. Third point, the IEEE 802 project further elaborates on the functions of the physical and data link layers of a network by breaking the data link layer into two sublayers: the Logical Link Layer LLC sublayer and the Media Access Control MAC sublayer. Together, these sublayers handle a media access addressing and control through the MAC sublayer and provide reliable error-free delivery of data frames from one computer to another through the LLC sublayer. And now let's go run back through the summary topics under the Introduction to Networks and Network Concepts, Network Design Essentials, Network Media, and Network Interface Cards. The discussions under Introduction to Networks and Network Concepts are the following: what is networking, network fundamentals, local and wide area networks, a networking lexicon, clients, peers, and servers, the network medium carriers, network messages, network protocols, network softwares, network services, network types such as peer-to-peer networking, service-based networks, storage area networks or SANs, wireless personal area networks or WIPANs, hybrid networks, server hardware requirements, specialized servers, and lastly, selecting the right type of network. Summary. First point. This chapter discusses the basic elements of all networks. This includes the presence of networking medium, cabling of some kind, and the requirement that any computer that seeks to access a network must incorporate a physical interface, network adapter to that medium. Second point. In addition to the hardware, computers must have a networking protocol in common to communicate, and they must have include networking software that knows how to use the protocol to send and receive messages or other information across a network. Third point, networks deliver services such as file sharing, printing, email, and other messaging services and much more to their users. Fourth point, you learn about four basic types of networks: peer-to-peer, in which any computer can function as either a client or a server as circumstances dictate; server-based, in which users act as a client of dictated machines that take the server role; storage area, in which network storage is centralized and data transfer occurs over high-speed links for faster access; and hybrid, which incorporates peer-to-peer and service-based features. Fifth point, you're also introduced to a developing network type called a wireless personal area network or WPAN, in which the network is limited to a small area around a person. Sixth point, budget number of users, types of application or network services, and requirements for centralized administration and control are the major criteria you should apply to decide which type of network to deploy in any given situation. Not only do servers require specialized hardware and software. Seventh point, not only do servers require specialized hardware and software, they also are capable of taking specific roles, acting as file and print servers, fax servers, email servers, application servers, and so on. The discussion under network design essentials are the following: network design, designing a network layout, standard topologies. These are bus topology, star topology, ring topology, and wireless topologies. There is also hubs such as active hubs, passive hubs, and hybrid hubs. We have also switches, variation of the major topologies such as extended star topology, mesh topology, star bus topology, and star ring topology. And also we will discuss selecting a topology and constructing a network layout. Chapter summary. First point, all networks build upon one of three basic topologies. Knowledge of these topologies and their limitations help ensure informed decision when designing a network. All networks build on three basic topologies: bus, star, and ring. Second point, the extended star topology is the most widely used topology in networks that contain more than just a few computers. As the name implies, the extended star topology is a star of stars. Third point, the bus topology, the most basic of the topologies, is easy to install but is an outdated topology that normally should not be used for new installations. Fourth point, the star topology offers centralized management and a higher degree of fault tolerance. A single cable or computer failure does not affect the rest of the network. The star topology is the topology of choice in today's network. Fifth point, the ring topology offers computers equal time on the network, but additional computers will significantly degrade network performance. Sixth point, a hub is a central point of concentration for a star network and passes electronic signals to the network. An active hub generates the signals. A passive hub simply passes them along. Similar to a hub, a switch offers greater bandwidth and intelligence and provides significant performance advantage over hubs. Due to these advantages and decreasing price on switch, they have become the device of choice in corporate star topology network. 7 point. Variation on the major topologies allow even greater fault tolerance and flexibility. The extended star in the most common, building on the popular star topology. Building on the popular star topology. The mesh is the most fault tolerant of all network topologies. It allows every computer to communicate with every other computer. A star bus or star ring lends the advantages of a star topology, its centralized management, and the best of the bus and ring topologies. Eighth and last point. A network layout should be consistent with the existing network and accurately maintained as the network changes. Many third-party tools are available to assist in design and maintenance. The discussions under network media are the following: network cabling, tangible physical media, primary cable types. And these are general cable characteristics, baseband and broadband transmission, the importance of bandwidth, coaxial cable, twisted pair cable, fiber optic cable, and cable selection criteria. Wireless networking in tangible media. The wireless world, types of wireless networks, wireless LAN application, wireless LAN transmission, 802.11 wireless networking, wireless extended LAN technologies, wireless MAN, the 802.16a standard, microwave networking technologies, and lastly, other wireless networking technologies. Chapter summary. First point. Working with network media, whether wired or wireless, requires careful attention to user requirements, as well as consideration of budget, distance, bandwidth, and environmental factors. Choosing an appropriate technology depends on weighing all these factors, meeting immediate needs, and leaving room for growth and change. Second point. For wired networks, the primary choice are between twisted pair and fiber optic cables. Coaxial cable is an obsolete for new land installations, but is still the media of choice for delivering cable television and broadband internet over cable to homes. Third point. Twisted pair cable comes in unshielded UTP and shielded STP varieties. UTP is commonly rated according to the ANSI, EIE, and TIA 568 standard in 6 categories, of which category 5 by 5E and 6 are the most commonly used in modern networks. STP has no longer rating scheme, but its shielding supports higher bandwidth and longer network span than UTP. Fourth point. New UTP categories include Category 6 and Category 7. Category 6 cabling is the recommended cabling standard for Gigabit Ethernet, while Category 7, if and when the standard is completed, lacks backward compatibility with other standards and will likely be used only in special situations. Fifth point. Fiber optic cable supports the highest bandwidth and offers the the best security and resistance to interference of any type of cable, but it's also the most expensive. Fiber optic cable is more sensitive to stress and bending and requires considerable expertise to attach connectors and install in general. Connector types include ST, SC, and a newer type called MT-RJ. Sixth point. Cabled network typically use one of two transmission schemes, broadband or baseband. Broadband transmissions use analog signals to carry multiple channels on a signal cable, where one channel is required to send and another to receive signals on most networks. Baseband transmissions uses only a single channel to send digital signals that occupy the cable's entire carrying capacity. Seventh point. Seventh point. Alongside cable Seventh point. Alongside cable-based networks, wireless networking assumes an increasing portion of the network load. Wireless technology works well to provide cable-free LAN access, to extend the span of LANs called extended LANs, to provide wide area network WAN links, and to support mobile computing needs. 8 point. A typical wireless network acts like its wired counterpart, that is, a network adapter transfers communications across the networking medium, except that wires are not needed to carry the signals involved. Otherwise, users communicate as they would or any other network. Wireless network use a variety of 9 point. Wireless network use a variety of electromagnetic frequency ranges, including narrow bandwidth. Ninth point. Wireless network use a variety of electromagnetic frequency ranges, including narrow band and spread spectrum radio, microwave, infrared, and laser transmission techniques. A pair of devices called Ninth point. Wireless network use a variety of electromagnetic frequency ranges, including narrowband and spread spectrum radio, microwave, infrared, and laser transmission techniques. A pair of devices called a wireless bridge can also extend LANs. Short-range wireless bridges can span distance up to 3 miles. Long-range wireless bridges can spread up to 25 miles. 10th point. The 802.11b wireless standard and its higher speed successors promise to make wireless networking commonplace in homes and in the corporate environment. The 802.11b standard specifies bandwidth of 11 Mbps, whereas the 802.11a and 802.11g standards specify bandwidth up to 54 Mbps. A new wireless standard, 802.16a, provides up to 70 Mbps of bandwidth over long distances, 30 miles, and can be used to create metropolitan area networks and provide broadband wireless access to metropolitan area network and provide broadband wireless access to outlying areas. 11th point. Mobile computing involves using broadcast frequency and communication carriers to transmit and receive signal using packet radio, cellular or satellite communications techniques. Finally, wireless networking appears poised to grab an increasing share of networking installation as newer and more powerful technologies and standards start to come online. The discussions under network interface cards are the following. Network interface card NIC basics, from parallel to serial and vice versa, PC buses, other PC interface used for networking, principles of NIC configuration, making the network attachment, choosing network adapters for best performance, special purpose NICs such as wireless adapters and remote boot adapters, and also we have driver software. Chapter Summary. First point, network interface cards and ICs supply the interface between a computer and a networking medium. Network adapters also prepare, send, and control data flow across the network. Second point, when sending data and when sending data second point, when sending data, a NIC must reformat outgoing data from the parallel form that arrives through the computer's bus to the serial form used over most networking media. To receive data, this process is reversed. Each NIC incorporates a unique hardware network address called the MAC address to distinguish it from all other NICs on a network. Third point, NICs include the configurable options that must be properly set for an adapter to make a working network connection. These options are usually automatically selected by the plug and play process, but sometimes they require specifying a unique interrupt request line IRQ base I over 1 over 0 base I over O port and base memory address. Fourth point, for compatibility, the NIC's edge connector must match the PC slot into which it plugs. Likewise, the NIC's media attachment must match the network medium and connector type to which it will connect. Fifth point, network adapters can exert a profound effect on overall network performance. Numerous performance improving options include direct memory access (DMA), shared adapter or access memory, and bus mastering can enhance the capabilities of such cards. Other useful enhancements including RAM, buffering, or incorporating on an onboard coprocessor to offload data handling chores from the computer's CPU. Network adapters can even incorporate specialized capabilities including hot plug, dual ports, security settings, management interfaces, wireless communications, and remote boot support. Sixth point, when purchasing a network adapter, consider the following checklist. Bus Number 1. Bus width. 16-bit is lower than 32-bit PCI or PCIX. Bus type. Pick 64-bit PCIX for servers whenever possible. Memory transfer. Shared memory outpaces I over O or DMA. Special feature required security management protocol handling hot plug capable. Special features required security management protocol handling hot plug capable. Bus mastering important for servers. And lastly, vendor factors: quality, reliability, staying power, and reputation. 7 point, when purchasing a wireless NIC, keep in mind the Wi-Fi standard that you want to use, such as 802.11a, 802.11b, or 802.11g. Also consider the type of security you wish to employ for the wireless network and whether the adapter supports the security standard in use, such WEP, WPA, and in the future 802.11i. 8th and last point, the driver software is the key ingredient that permits a network adapter to communicate with computer's operating system. It's essential to ensure that a valid driver is available for your operating system before purchasing an adapter. Even better, always obtain the latest driver versions before installing any network adapter. It it's all it's also good it's also a good idea to make regular driver upgrades part of your network maintenance routine. And that concludes the discussion we have for today under the topics of the following: OSI and 802 networking models, the IEEE 802 networking specifications, brief recap on the topics of the following: introduction to network, network essentials, networking media, and lastly, network interface cards. Thank you for listening.